Okay, lecture 6. This is our last lecture in our probability review, and we're talking about conditional expected value. And let's dive right into it, into the formulas. So, the previous lecture we introduced probability, conditional probability functions, and in the lecture before that, I forget now, we talked about expected value. And expected value is our weighted average of the possible outcomes. And in here, it's a natural extension of this expected value, this conditional expected value. So we can condition on events or random variables, and this conditional expected value is just the weighted average of our possible outcomes if we condition on specific events or if we condition on specific random variables. So we can think of two conditional expected values. We have our formula for conditional expected value if we condition an event A, and we have our formula if we condition on a random variable Y. And I believe in here, I don't think I gave a precise formula for this conditional distribution function or conditional density function. I only gave the formula of the case of random variables, but in this case, you can think of this as the case where y is equal to the indicator function of a. And in here, to be more specific, you can think of this random variable given an outcome omega. This is going to be equal to the indicator function of a omega, which is equal to 1 if omega is in A, or 0 if omega is not in A. And this works for both cases. So if you introduce this random variable y, which is an indicator function of event A, then you obtain this expected value. You obtain the conditional probability functions given the definition we gave in the previous lectures for this quantities, and then you can obtain this conditional expected value. And in most cases, we're just gonna focus on this formula when we're conditioning on a specific random variable. And a particular interpretation that we can have for this conditional expected value is that this is our best approximation of a random variable x given this event that y is equal to y or an event a. And in the typical expected value, the one that we define without conditioning, that corresponds to approximating x with no information. We're not conditioning anything, and in that case, the best approximation of a random variable x, if we have no information, is just going to be the weighted average. And in here, for conditional expected value, the way that it works, approximating given an event, is that if we're given different values of y here, then our best approximation is going to be different. And for instance, if we go back to the previous lecture where we had this cartoon of conditioning on different values y2 and y1, and if we're given the information y1 and we want to do the best approximation of x, then in this case, the best approximation is going to be some expected value somewhere here. But if we condition on a different event on y2, the best approximation is going to be somewhere in here. It's going to change. So given the information we have, our conditional expected value is going to react to that, and it's going to approximate a random variable differently. And it's going to be the best approximation has to adapt to the information that we're given. So whereas before the expected value, when the original definition of expected value, the one that's not conditioned, or the one that has no information, that is a static or constant or a numeric value. That's just a number. But for conditional expected value, turns out that it's not. You can think of it more as a function on y, and it tells you that it's going to change your best approximation or your conditional expected value on your value y. So, and I'm going to try to flesh out this idea and make it more precise in this lecture, or technically. And in here, one of the properties of this conditional expected value is this law of total expectation. And this is similar to the property of law of total probability, when we computed the probability of a certain event by considering different cases and considering the conditional probability of given each case and weighing it by the probability of that event. So another way that you can rewrite this is y, and this is in the discrete case for simplicity, but this is expected value of x given y is equal to y times the probability of y is equal to y. So again, we're thinking of this as a function on y, and we're considering all the approximations of x given different events y, and we're doing a weighted average of those conditional expected values. And here I have the proof of this formula, that this statement I should have mentioned from the very beginning is that the law of total expectation is that the expected value of the conditional expected value is the expected value of x. So again, this is a function on y, and if we average over all the values of y, we're gonna get the expected value of x. And y are the different values of y are the different cases that we consider for our variable x and how it depends on it. So let us go through the proof. And in here, again, we think of this as a function of y, and we take the average values of, we take a weighted average of this quantity. So we plug in different values of y, and we weigh it by the probability of y equals y. And in here, I use the definition of conditional expected value given in the previous slide. And I then use this formula for the conditional distribution function given by this, and I note that this times this is equal to this, and I have this summation. And now I have this formula for the marginal probability distribution of x, which is the summation over all y. So I remove the summation over y and transform this to the marginal distribution function. And now I have the definition of expected value of x. So in here, the result is that the expected value of the conditional expected value is equal to the expected value. And again, this is a specific way to break your problem into different cases. And these are cases parameterized by the random variable y. And the way that I like to think about it is through this first line. So if I want to compute this expected value, then I use this formula to compute it if I want to break it up into different cases. So now let me go to a characteristic property of conditional expected value. So I've given you a constructive definition of conditional expected value using the conditional probability function. So this formula is constructive. So once I'm giving you the probability the conditional probability, then you can just plug in this formula and compute it. But alternatively, you can characterize this conditional expected value by these two properties that we have here. So let me just go through it. We have random variables x, y, and z. And the first thing that we assume is that there exists a measurable function. So a map from R to R whose inverse image of measurable sets are measurable. And you can go back to lecture 1 to review the definition of measurable, but in most cases, just think of measurable as continuous or piecewise continuous functions, and take a function g so that z is equal to g of x, and you have this property that z is a function of x, and you take the second property that the expected value of h of x for any measurable function h times c is equal to the expected value of h of x times y. Then we have that z is equal to the conditional expected value of y given x, which is just g of x. So first remark, well, the 0th remark is that what I changed convention from the previous slides. Before I was conditioning on y, and now I'm conditioning on x, but that's just because I forgot to double check. But the first remark here is that from our discussion in the previous slides, we have that this conditional expected value is a function of x. The way to think of it is that it has to be a function of x. And in here, what this is telling us, or the content of this claim, is that this is picking out which function of x it is. From our discussion, we know that this expected value of x, this expected value of y given x is going to be a function of x, but we haven't said which function of x it should be. And the way to pinpoint which function of x it is through these two properties. So first of all, the first property is almost automatic. We know that the expected value, the conditional expected value, has to be some function of x. So this is just kind of reasserting that condition. And the second assumption is that this identity holds. So this is really what is pinning down this function g of x. And in here, the thing that makes this condition restrictive is that this is true for any measurable function from R to R. And this pins down this function of x. And so let's see how this works out in the proof. So again, the constraining part of this is that this is true for any measurable function h, and in particular, I'm going to pick a very precise function h. And in here, I pick h of x, which is going to be equal to 1 if x is equal to x naught or 0 otherwise. In shorthand, I can use indicator functions and write this x is equal to x naught. So I use this specific function h, and I want to leverage this assumption. So first of all, I have the expected value. I start from here. I have this expected value, and then I use the first property to substitute this. And I have this. So I have this expected value of h of x times g of x. And since h is equal to 0 if x is not equal to x naught, then the only term contributing to this weighted average of h of x times g of x is when x is equal to x naught, and in that case h is going to be 1, so it should be really 1 times this. and then we weigh it by the probability that x is equal to x naught. So we have that the left-hand side of this identity, expected value of h of x times c, is going to be g of x naught times p of x naught. Now, we want to compute the right-hand side of this equality, and this is going to be expected value of h of x times y. And here I just use the definition of expected value using the joint density distribution. And then, moreover, I use the definition of the conditional distribution to rewrite this joint into the product of conditional times marginal. And then this summation over y, I can recognize that this is going to be this summation over y. This is, I can factor out this x naught over here, and I have that this is equal to expected value of y given x is equal to x naught times probability that x is equal to x naught. So just to recap what's going on, we've computed this left-hand side and it's equal to this, and we computed the right-hand side and it's equal to this. And by the second condition, that means that the left-hand side is equal to the right-hand side. So that means that this is equal to this, and on both sides we have a factor of p of x naught, so I can cancel it out, and I have that g of x naught is equal to this summation, and this summation is the definition of the conditional expected value. So using this clever choice of h, since this is true for any h, I can pin down the function g, and this is going to determine my conditional expected value. And this is actually a axiomatic definition of conditional expected value. And in the theoretical treatment of probability theory, conditional expected value is actually defined this way, using these two properties. And then you then derive the constructive definition that we gave above. But if you want to determine the conditional expected value of random variables, then you have two ways to do it. Either you can show these two properties, or you can compute it directly with the joint density or the conditional density and conditional distribution. But this turns out to be very useful, and in most cases for working with abstract random variables, these properties tend to be very helpful. And now to wrap up this lecture, I'm going to go through a few properties of conditional expected value. And these are the three main properties that you need to work with conditional expected value. First is linearity, and these are also properties of expected values. These properties extend to the conditional case. So we have this linearity property that that you can factor out the summation and multiplication of this expected value if you condition x, and you just carry out the conditional expected value. And this is for alpha and beta, some constants, and this is for every alpha and beta constants, and for every random variables u, v, and x. Independence, and these are actually properties that don't really come from they're not in expected value, because you really need the conditioning on other variables. But in any case, but actually, before I go back to this other two properties, I worried about proving. I'm not proving this properties, but there's two ways that you can prove this. You can either prove that use the constructive definition or prove the characteristic definition showing properties 1 and 2. So you can show that the left-hand side satisfies property 1 and 2, and the right-hand side satisfies properties 1 and 2. And since these two properties characterize your conditional expected value uniquely, then they have to be equal to each other. And it's a little bit more of an abstract argument, but it tends to be less messy. And we have these two other properties of conditional expected value. First is independence. If y is independent of x, then the conditional expected value of y given x is just equal to the the expected value of y. And this is consistent with the interpretation that the conditional expected value of y is the best approximation of y given x. And in this case, if y is independent of x, then that means that we have no information of y if we're given information of x, since it's independent of x. So the best approximation that we can do is the best approximation we can do with no information, which that is just the regular typical expected value. And in particular, if we change values of x, then our conditional expected value can't change. So it has to be some constant. So changing the expected value of x cannot change our conditional expected value. So it has to be some constant, and it has to be the best approximation. So that constant has to be the expected value of y. And this is the type of thinking or the type of argument that's implicit through this definition, through these two properties. And on the other side, we have the complete dependence, meaning that if y is a function of x for some g of x, then we have that the conditional expected value of y given x is just equal to y. And this also is consistent with these this interpretation that conditional expected value is the best approximation given x. And in here, if we're given x and we want to approximate y, well, we know how y depends on x, so we can just compute y directly. So we have that y is completely determined by x. So the approximation is just the value of y. So if we're given the value of x, we can just directly compute the value of y. So our conditional expected value is going to be y. So these are properties that are important for working with conditional expected value. And you should keep them in mind. I think that's the end of this. This is the end of this probability review. We'll continue with another set of lectures about Markov processes, but this is just a brief and quick review of probability that is most pertinent to this stochastic processes and random processes. Thanks for listening to these lectures.